computing engines, and actually we used to ride the wave of the process technology, looking at using Moore's law as our drive, and by us adding a new architecture. But then Moore's law is starting to end, and Dinard scaling stopped us from continuing riding this wave. And luckily, very luckily, there were killer applications, and I'll explain what is killer later, started to appear, and the implications are really vivid. And then, we have to look at energy and energy efficient. And then I'll give a part which will be more on the trend towards heterogeneous and accelerators, a non-normal machine, and that will be the first part. So let's jump into it. So all of us saw this line of feature size versus years. Here we show only till 2016, but we know that today we have already a feature size of 5 nanometer. By the way, there is also some companies are starting, and TSMC also starting to work on the 3 nanometer. Actually, the volume of 3 nanometer was already quote unquote bought by the big companies, meaning everybody is waiting for the next generation of process technology. But in general, what we see here, that at one point, which is about year 2000, the slope started to drop even faster, and that was a decision at the time that Intel made, that every 2 years to have a new process technology. And we all know that from process technology one to the other, we wanted to see the feature size reducing in 0.7. So so we reach where we are today. By the way, if we look at the right side of the graph, there is a delay, dramatic delay, definitely by Intel and others, in producing a new process technologies at the range of 10, 7, 5, 3. And definitely we are at the edge of ability to reduce feature size. By the way, all of us understood, even just to add some information, Gordon Moore, that founded Intel, at the end, he said several times, who was, the guy who started the concept of Moore's law, and he said that every exponential growth have to stop sometime, and that's where we are today. So if we look backwards at performance history, and this is interesting to see, in the past year, when you look at the feature size or the relative performance versus feature size, we see that and by the way, pay attention, on the left side, it's a logarithmic scale. And what we can see that the process technology gave us about 100x, going from 1.5 micron to 32 nano. The process technology by itself gave us a factor of 100x on the relative performance, while the architecture, the building of the concept of architecture gave us something like about 30. So altogether, 30 or 20, depends. The multiplication of these two should be the 2000 that we got. So there's a mistake here. But anyhow, the basic idea that process technology was driving the performance line in the last 30 years, and even more. Architecture gave something, but only about a third or so. So so we, the architect, did okay. But if we are looking at the most famous graph of Moore's law and data that was collected by Mike Horowitz and his guys in Stanford, what we can see here that, you know, process-related increase in the years, right? It was growing exponentially, right? And we know that if we are looking at number of transistors, it went exponentially high. But we are seeing here, you know, lately kind of a bend in this maximum transistors that you can take care on a single die. And we'll talk about the process technology and the power in a minute. Another thing that we are seeing, which is very, very dramatic, is the process technology nowadays. The frequency of operation is starting to saturate, and so we are between, you know, 1 gigahertz to 10, but it's plateauing in the last 10 or 15 years. So this is the process doesn't enable us to go much further from now in number of transistors and in frequency. And if we look at the architecture related, what we see here is a graph of a single threaded performance. You know, in this case is you know, spec as a benchmark of spec integer. So that means this graph, this saturation with this graph, said something about our ability, mental ability, to bring new ideas to the table of the general purpose microprocessor. And you know, since I was in this time around, it was very easy to bring new ideas to something that that was not close to saturation. So every idea that we brought at that time was substantial in the performance impact. And today it's much more difficult to continue the wave. And in a sense, what we're seeing kind of a plateau or saturation in the single thread performance. Another thing that we can see is that, you know, long time ago, meaning in the 90s and 2000, you know, we didn't reach the maximum typical power that can be cooled down, a die cooled down, you know, and all of us know that at around 100, 150 watts, you can cool it with air cooling in a regular air cooling. But the minute you go above 150 watts towards the 200 watts, the air cooling becomes much bigger and much more complicated, as you can see in NVIDIA processor on cards, which, you know, the heatsink there is much bigger than the electronic below. And we are reaching kind of a plateau here when we look at the microprocessor that exists. So this is a kind of the situation from the technology point of view, at least on the silicon side. There's another a problem, and a problem much more vivid than we expected, the power wall. And if we look, all of us know the equation of power, CVF V squared. And if we know that we are going from one generation of processing to the next one, from n to n plus 1, right? and we keep the same die size, what usually until now, what we got double the number of transistors, and if we keep the same area, the capacity that goes when we go from one process to the other until now was about 0.7x, the capacity per transistors. The voltage, which is the main part that help us reduce power, went from one process generation to the next process generation in about 0.75. All of us, or some of us still remember that we have 5 volts and 3.5 volts and so on. And today we are below 1 volt. And the frequency usually went up to 1.54x because of the process technology. Nowadays, when we are looking, and now we are looking at the right side of the graph, by the way, if we look at those numbers in general, and you just now do the power equation, you get that the power increase per generation is about 1.1. That meaning that if we have some ideas how to save power, enough that we save about 10% of the power, then we can go from one generation to the other, while the power dissipation of this element stayed the same while going from one generation to the other, while keeping the die size constant. If we go now today, again, moving from one generation to the other, process generation to the other, we increase the number of transistors by 2x. Let's say that we keep the die size constant. The capacity is the same as before, 0.7x capacity per transistor. The main change is that the voltage is not changing as much as before. Remember, it was 0.75. Now it's more close to 1, actually, because we are getting much closer with the power supply to V threshold. And the frequency is not growing as fast as we expected and as fast and we got in the past. And what we are getting here, if you look at the equation, the simple equation of power, we're getting that the power increase per generation is about 1.5. And that means if you had your processor at one generation, let's say in 80 watts, and you build a new processor, the same die, meaning you double number of transistors, and you go to the next process generation, you probably will get 120 watts. And the next time, you'll get 180 watts. So we are reaching, and as we talked before, we're reaching the plateau of ability to cool. And that means that not all transistors, and this is the end of Dinard scaling, what we call, that means that not all the transistors on die can work at the same time in the highest frequency possible. So there are two happening that we encounter, and one of them is the Dinard scaling, as we said, right? That the process technology doesn't support any more the power reduction that we enjoyed for so many years, and the feature size reduction is kind of stalling. And if you look at the microarchitecture, in general case, what happened, many of the ideas that we had in the past, we don't have anymore because we use most of the ideas, the easy ideas, and probably at the end of a process like that you are working for so many years to try to get ideas out. From time to time, after many years, you end using the simple ideas, and the complex idea are not so easy to implement, definitely power-wise. Okay. Before we go to next foil, any questions around?
No, Prof.
I didn't hear. Okay, so let's continue. Energy wise, this is a foil that again Bill Daly and Mark Horowitz from Stanford used to use, but it's a more than just yet another foil, but it's if you look at the numbers, you can understand the message, the big message about the energy. Here we are talking about energy number for 45 nanometer technology, and we talk about LU that does the integer add and integer multiply, floating point add and multiply for 16 and 32 bits, memory accesses, to cache, right? If the cache is, and here we're talking about access 64-bit, and we talk about the small cache of 8K, 32, 1 meg, and DRAM. And if we look at the instruction energy breakdown, in general, we take here an example of instruction that actually, instruction of add two numbers or two register, the two numbers in registers. So let's go and look at that. So first of all, the add itself, right? That and in 45 nanometer, right? When is about 1 picojoule. So the purpose of the instruction to add two numbers cost us about 1 picojoule. But remember, in order to do this add instruction, first of all, I have to access the instruction cache, which takes me about 25 picojoule. Then I have to get into the register file, and it costs me another 6 picojoule. And the control, the decoding, prefetch, and so on will cost me the rest. So the overall instruction, including the add, will cost us about 70, the energy that will cost us about 70 picojoule. And remember that all we wanted is just this add, which actually costs only 1 picojoule. So there are about 2 orders of magnitude energy waste in every instruction we do. So this is one thing to remember, that the instruction-based architecture that we built for many years, energy efficient was not at our most important thinking at the time. But what we got here, we got a lot of flexibility. The instruction set architecture in computers enable us to have actually to write any program we want, to make any computation that we want in general, and it give us a lot of flexibility, but energy-wise, we are not very efficient. If we look at the computing elements and the memory, it jump into your eye. The first one is the DRAM access. And if you look, for example, going to 1 meg cache, right, cost you about 100 picojoule, but going to DRAM will cost you about an order of magnitude more, even more than order of magnitude, right, about 20x. And this is you have to raise a big flag. A DRAM in general is not a very efficient energy-wise element. Remember, one thing that we did with DRAM is actually what we have to refresh it every time. And by the way, one of the research that we did in past, trying to reduce accesses to DRAM as much as possible, and I'll show some hint to that in the next foils. We created concept in which you are not, your access in the DRAM not very frequently, and we almost didn't save, or we didn't save a lot of energy, because about 50% of the energy of a DRAM comes from refresh. So even if you don't touch the DRAM, you don't read it ever, you pay a lot of energy just to keep it alive. So that's interesting to see. So the messages here is DRAM is expensive, right? You know, if you don't need to use DRAM, don't, right? And we'll show it later when we reach machine learning. We'll show it. In some cases, some ideas to try to reduce the DRAM in general in system, in order not to waste energy. And the other is, again, we'll show it also in the machine learning. Instruction set architecture is not the most energy efficient concept. It's very wonderful as a flexible way to implement things, but not very efficient energy-wise. Okay. So the insight here from this foil is the programmability, which means the instruction set architecture bring us to something which is not very efficient. That's all. So that's for you to know. So let's go to something that actually is trying actually to grow and actually probably will keep here and there the programmability, but will reduce the application range. And we'll talk about heterogeneous computing, and we all know about heterogeneous computing, but we like to emphasize here a couple of strong messages behind. First of all, we all know, we're all using, those iPhones that and equipment that simultaneous. There are a lot of different programs running in the same time in the same environment. And the range of the programs that we are using span widely in their requirement and behavior. So some of them are more compute bound, and some of them are more memory bound, and so on. And is it really so wide? And if we look at the application driven implications, that there are core structure which it's for example, if we use one core that runs the instruction set architecture, that means that when you start already, you are not very efficient energy wise. There's inter-core communication between the core, data access, and the memory wall. We'll see it more and more. We see it already, but we'll see it more and more when we talk about in the next hour, when we talk about machine learning. We'll see that this is a really a big limitation in getting performance out is the memory wall. And as I said, it's not so much the multiple core that calls for rethinking about the memory subsystem, but I think the performance that we are getting, the more performance we need to get from the computing elements, the more memory we have to access. Because the more computing you're using, definitely you need the data to get the data from somewhere. And so definitely the memory subsystem, we have to work on it, and we have to understand the limitation and the implication. And communication to the data source, that's definitely depends on what we are working in, which environment we are working. communication to data source. There's a data source somewhere that we have to access, and the acceleration interaction between CPU and memory. That's several elements that when we talk about acceleration, and I like to show that, you know, the system that we are working, the application that we are using, they are, although all of them are doing computing, and in this case, where I'm showing all kind of flying machines, they're all flying, but they are all so different from each other. And the same thing when we talk about application. We have many applications that span all over, but the application are very different from each other. And that's the we have to remember that, you know, and what we are trying, or what we did in the past, we took this application and run all of them on the same engine, the general purpose instruction set based architecture. And then many times we complain about energy, about, you know, performance and so on. But definitely, you know, taking all the application, or the different application, and running on the same architecture, what we call, you know, one size fits all, doesn't work anymore, because we need more performance for all our applications. So so the implication, at a time, you know, the people were starting to talk, at least the market was going there, talking about, okay, let's add more cores, and by adding more cores, we'll get more performance. And multi-core was an intermediate remedy to the problem of performance. But remember one problem: the minute we go to symmetric, you know, homogeneous solution in multi-core, the performance per power stay the same. If you add 2 cores, you probably, not always, you get double the performance if there is no conflict, access to memory, and so on, and dependencies. But power, definitely you double the power. So in a sense, the performance power that you are getting is staying more or less the same, and usually is going down a little bit. And the long term, it's not long term, actually, it's today, is to go to asymmetric, to heterogeneous. And special purpose hardware can reach, you know, between 1 order to 3 order of magnitude better performance power than the general purpose hardware. And I showed you the amount of energy that we are wasting when we have the wonderful flexibility of instruction set architecture. If we stop using it, or we stop being dependent on instruction set architecture, we maybe, and we do it already, build an accelerator that the power efficiency is much better. And the implication are accelerator in every system, and you know, every computing element that we have today, there are accelerators inside. So, but in order to show why it's so vividly strong, I wanted to show you something. And since I was in when I was studying, my master thesis was in analog electrical engineering, and at that time there was a concept which we call a gain bandwidth product, and we'll talk about it, and then I'll take this gain bandwidth product and try to give an analogy to the application level and what are the implications. So what we did in the past, this is in the analog time many years ago, if you look at the graph of gain versus frequency, and we're talking about, accelerator, not accelerator, but the amplifiers that we check their gain. So in general, at that time, in order to get some level of acceptable gain, you had to reduce the frequency of operation of this device. So we got the bandwidth, we got the gain, and the question is, what do you do next? What happens if you need, a range of frequencies around here? But before that, the concept of gain bandwidth was that if you want a wider amplifier that will respond to a wider range of frequency, definitely you have to get or to give up in the gain. So the multiplication of gain 1 times bandwidth 1 was more or less the same as the multiplication of gain 2 times bandwidth 2, what we see it here. So we call it the gain bandwidth product, which stay constant in specific technology. And what do you do if you want to get an amplifier which are wide, that respond to wider frequency of operation? So what you do, you usually add those different amplifier, put them all together, right, and add them up. So in general, what you do, you take amplifier 1, amplifier 2, all of them getting input of the signal, and you sum up the output of the signal of the amplifiers, and you get something which is had a wide frequency response and pretty good gain. So this is what we are talking about in our field. And I'll try to give the analogy here. And in the application domain, we are looking at it's running too fast. We have application range, and we have the performance per power. So what you can do, you can build a machine that will have a wide application range, but then it will get performance power which is not so good. And you can build something, or engines, that will have a narrow application, that will be able to work on a narrow application range, but to get much better performance power. So if you look at general purpose architecture or instruction set architecture, it covers a very, very high a range of applications, but the performance power is not great. We all know about it. And the minute you narrow it down, you get much better performance power. So that's the concept that we are here. And actually, when we talk about the range of ideas that we have, the bigger core you build, with the higher performance you get, you'll get probably a wide range of application, but the performance power is much less. By the way, the performance power is being reduced because when you like to get a better performance, you do more speculation, and speculation in general reduce your performance power. And if you go to a small core with not a big performance target, and then you do less speculation, and probably get much better performance power. And definitely when you go to accelerator which actually respond to a narrow application range, right? Now the game that we are playing, all of us, is how wide is the application range? This one, is it graphics, which actually a pretty wide application range? Or if you talk about, neural net, for example, the narrow is the application range is much more narrow, because in graphics you have instruction set, and you can almost get any program running on it. Not very efficient, but for some cases pretty efficient. And so the minute you narrow it down, you get a better performance power. So, so we are going to look at the application range, and now let's try to go to a place, we call it a multi-amdal. It's a concept that is super interesting, and because of that, I would like to show you. And the main question was, if you have limited resources on your die, for example, and you have several accelerator or elements that you like to use the area for, and the question how to divide the area between the different accelerator in order to get the best performance that you have. And we are reaching this concept again and again and again everywhere we go. For example, you have a limited power or limited energy that you like to that you can spend on a specific element, specific energy. And the question, okay, and you have on this element several accelerators, how will you divide the limited energy in order to get the maximum performance, for example? This is a one idea that Mark Hill did in the past when he talked about big core and small cores, and he came to some equation that talk about the speed up. But what we wanted to show is something else. The question that we have, you saw this heterogeneous graph and application range and performance per power, and you know this graph already. But remember, you can add another axis to this graph, and the axis is the axis of performance. So you have the performance power in one axis, you have application range. Well, until now, we saw only those peaks for the one with the narrow application range. And for general purpose, we got, a wider application range, but much less performance per power. But if we look at another axis, which is the absolute performance we are getting, and we just talked about it before that, between the big core and small cores, what we can see that the more you go with performance, there is a reduction in the performance power. And this is why, for example, it's not why, but this show very vividly in when we talk about small cores versus big cores. And the question now, when I have this many accelerators, what energy or what area, for example, to give each one of the processor or the accelerator in order to get the maximum performance. So that was the question that we were looking for, and we applied to one of our students, by the way, a master's student in the past. Anyhow, so what we say to him, something very simple. We said, okay, let's say that we have, this is time, and there are different programs, and one program takes about T1, a time of T1, and one program have a time of T2, and so on. I think we are missing here something. Just a minute. Okay, let's continue. So what we have here, we have programs that takes, each one of them are sequential to the other, and they take T1 cycle, T2, and so on, Tn. And the question, let's say that each one of those period of time is running different application range. So if we put an accelerator to T1, to the application range of T1, and another accelerator for the application range of T2, and so on, the main question is, how to reduce the time when you have a limited resources. So this is what we did. We said, okay, here's the time. On a regular system, we have the times is the sum of TI, and the TI is actually the sum of T1, which is application range, a specific application, T2 another specific application, and so on. And to each one of them, I can build a specific accelerator. Example, T1 can be graphics, T2 can be media, and so on. So for each one of them, we'll build an accelerator, and the acceleration function, F1, actually is 1 over the acceleration function, right? It really depends on the area, for example, the area that we have. So it's F1 of A1. So in a sense, the minute we'll run this application, let's say, for example, graphic, on a graphics processor with the area A1, I'll get a new time, which is T1 times F1 of A1. And the same thing for another accelerator and so on. And let's say that the sum of all the area should be limited to A. And actually what we want to do is to get a minimization of the sum of TI, FI of AI. So our target was increase the performance by reducing the time by increasing the performance within a limited area when you use accelerators. And when we did that, the student came back and said, hey, this is actually a Lagrange multiplier. And the result that we got, that in order to get the same, in this case, the same performance under a limited area, the TI times the derivation of FI of AI should be equal to TJ derivation of FJ AJ. Very interesting concept, but well known in the finance industry. If you are interested to look, it's very interesting that they're using some kind of this concept. And the question is really, how do you allocate the power for different units? You can play with it for power. You can play with it as a limitation of power, limitation of area, limitation of energy, and so on. And so what we did, we use it for power, for example, just to show, a case study. And what we got, we wrote the equation for the power, the average power, which is static and dynamic divided by the time. Anyhow, when you go, and then we decided to say, okay, let's have 3 programs that are running on 3 accelerators. By the way, we choose those programs because we had some paper that wrote about those application running on special purpose hardware, and the impact of energy depends on the size. So we took these 4 programs and we said, okay, we have 4 accelerators. One thing that we added is that 10% of the benchmark is executed on CPU. So we will use the multi-Amdahl and try to get the result. Here are the numbers that we got from this paper that talk about, power efficiency and area efficiency. And then we ask ourselves, okay, what will happen if we have this kind of a system? what is the size of the program, or size of the accelerator. What is super interesting, and look at the result that we got here. What we were saying is that if the budget, the number of transistors that we have is growing, but in this case, we took order of magnitude increase in the x-axis of the number of transistors, and we ask ourselves, what's the distribution of the transistors, and this color is for CPU, and then we have accelerator 1, 2, 3, and 4, and we ask ourselves, okay, if I'll provide you with more transistors, what will be the graph? And the graph shows something super interesting, which is growing. The minute you have more transistors, it's better to spend the energy, or in this case, not the energy, but the area on the big core, on the CPU. Intel liked this graph very much, because when we are talking about increasing the number of transistors, the CPU became more dominant if the axis is number of transistors. And this because, it's Amdahl, as we all know, because of that we call it multi-Amdahl, that the minute you improve the performance of, in the Amdahl law, the parallel parts, you have also to improve, eventually, the performance of this serial part. What is interesting that when we took the same concept, right, of multi-Amdahl, but now we look on the x-axis about reduction in power budget. So we took 2x, 1, half, and so on. What we saw that the power distribution is going down when we talk about the CPU. So suddenly, when you talk about an element like that the power is limited, definitely what you would like to have, you would like to have more accelerator, or efficient accelerator, versus the non-efficient CPU. So let's go a little bit faster. This is the summary of the multi-Amdahl, which is interesting, and we are using it, by the way, in many applications that we are looking. Also in one of the startups that I'm working, we are using it in order for multimedia and so on, because it's a very strong concept about, when you have limited resources, how to share them when you have multiple elements or accelerators. So another word about what's happening around us is the big data environment, and we all know about it. And in a minute we will talk about the solutions. And in general, what a message we have here is that usually when you are looking big data, at the end of the game, you do some analysis on the big data, and you have to get some result from the big data. So in a sense, there's a lot of data that we are collecting, and then we like to come up with some result of this big data. Usually the result is much smaller than the big data. And since the big data is so huge, our conclusion is that you can revisit this big data again and again. And what do you do usually is you do what we call read once. And we started quite a lot of research on that direction, but I won't spend the time here. In general, when we talk about ETL, extract, transform, and load, you have the structure of actually reduction of data a long time. Another important element, and then we'll jump, we'll go to the neural net. As we said before, as you remember, In instruction set architecture, we talked about 70 picojoule on the instruction in general, while about 1 picojoule we are using, or even less, for the add operation. The minute will go to a technology that doesn't have the instruction set architecture, and we'll talk about neural net, which does it, then we are saving those accesses of control and or this waste of energy in control and instruction case access, and we are ending up with having the register file access or whatever access to data and the operation. So suddenly, when you have a data flow architecture, and we'll talk about it later, a data flow architecture versus instruction-based architecture, we are reducing the energy that goes for the flexible instruction set architecture, and we have to look at it totally different. Then the data access become the majority of the energy, in this case, about 6 picojoule versus the operation, which is 1 picojoule or less. So suddenly we have to look at, when we go to data flow architecture, we have to look at the different requirements that exist because we are getting rid of the instruction set control and instruction access, a waste of energy. Okay. And many times we call it the read once counts, because in a read once, you don't need the instructions. Okay. And then what happened? So we saw several things. The technology is stalling. The concept of a general purpose architecture or the ideas in general purpose architecture is stalling in one way or the other. We have the big data problem, right? We have the problem of dividing the energy that we have. And the question all the time, while I was at Intel many years, that Andy Grove, the CEO of the company, used to tell us all the time, give us killer app. In killer application, his definition of killer application were new application that the old architecture or the old microprocessor couldn't handle, and we have to build a new microprocessor that will handle those applications. In this case, he increased practically the replacement rate of customer that buying new microprocessor, new computing engine or PC when there are new application or killer app. So let's look at in general, when we talk about efficient machine learning architecture or accelerator, in general, the minute you need a lot of performance, we know that we use a lot of energy. And remember one thing, that what we are trying to do in machine learning is in implementation of efficient machine learning is actually to map the hardware towards a graph mapping. And this is actually a data flow. Data flow means that you take the problem and you map it to a kind of a graph mapping architecture. And by that, when you have a data flow, you lose some of the flexibility, but then what you can get much better energy efficiency, and we'll show something about it. Just remember, when you build a data flow architecture, you have to, and we'll talk about it later when we talk about machine learning, you have co-designed the hardware architecture with a smart compiler. This one thing that not all the machine learning architecture companies were successful. You have to go, it's a software, it's a real software and hardware co-design. There's almost no flow control. You know, the branches that we are used to have in general purpose architecture doesn't exist. And what is most important is that it's statistical results. So you don't have, you know, if you manage to find a way to get approximate computing, you don't need to validate the execution. Okay, what happened is that, you know, this is an era of machine learning, and killer applications are everywhere, and everything is funneled down to machine learning, and we encounter more and more applications that are good for machine learning. And this is the second part of the presentation, which will cover the first part of it, and then we'll go for a break. So, machine learning basics. So first of all, what it is good for. It's good for, we know at this point, you know, for many other, but the main themes are vision, natural language processing, and recommendation system. There are other things, other workload, but they are less dominant like those. When I'm talking, and when we will talk about machine learning, I mainly talk about the vision, because this is the work that we are doing, and this is the most advanced workload that we look at in machine learning. NLP is getting speed up, and also recommendation system. For each one of them, what is the task? You know, we can see it here, and what kind of networks that they are being used, and we'll explain in a minute what are the networks and what are the basic primitive, just for your reference. Okay, what does the brain, how does the brain works? And we have the neurons, right? We have the axons, and we have inputs that are coming for the dendrites, and you have neurons that actually sum the inputs that he's getting, you know, giving some ratio to each one, and then send a signal to via the synapse and an axon to the synapse and to another neuron. So in general, just to let you know that in our brain, you know, there are about, you know, almost 100 billion neurons in our brain, and the neurons are connected by about 10 to the 14 to 15 synapses. So there's quite a lot of information running there. As I said, you know, the neuron receive the inputs for the dendrites. Here you can see that, right? And actually produce the output on the axon. So this is there's a synapse a weight which enable to control the influence strength. So in a sense, when there's a high weight to some of the inputs, its ability to impact the axon, the signal is higher. So that's the concept of the brain, and the deep neural net, what we call, actually loosely models the brain, and neural network. We'll talk about the computational approach, what we are doing there. Actually, what we build there, it's a large collection of artificial neurons, and each neuron aggregates input from inputs of or outputs of other neurons, and transmits the output to the next one. So there are layers of neurons, and we can see it here. You know, we call it deep neural net because there are multi-layers. It's not only one or two. And what we can see here in this case is the input, and here we talk about, again, I'm talking mainly about vision. We are looking at the input, at retina, and so on. And then there are layers of the neural net that actually do the quote unquote computation in order to get the output. And you can see it also in this picture that show the retina and so on. Okay. So in order to emulate what the brain does, what we are doing is actually getting the inputs, right, from the neurons that are a layer before us. And actually what we do, we actually multiply them, the data, x0 by w0, and we sum all the inputs into one actually element, a summation element. So there's a multiplication here, there's a summation here, there's kind of a bias that we are getting, and then this is a nonlinear activation function that is the output and sending to the next neuron. So this is the basic computing element that we see in neural net. You know, in some neural nets, and if you're looking at, where is it? If you're looking here for the NLP, there are some elements which are more complicated that we are showing here, that have some memory here. But we are talking, now I'm talking about the elements only of vision, and the most useful element, computing element that we have. By the way, the nonlinear function is taking the output actually and change it to actually a positive only signal. So actually it's zero out all the negative that we have, a negative element or negative output, and actually, and this is usually called, the red one called the value, which is the most commonly used. So that's the computing element that we see here. Okay. Now what we do is as we said, we do a weighted sum. There are different inputs, you know, input 1, 2, and 3 in a layer, and we are the structure of neural net is layer by layer. So we have layer 1 and hidden layer or layers and the output layer. And in a sense, what we are doing, we multiply the input by the weights, right? Add them together in the hidden layers, and then we go to the output layer. You have to remember that not all the connection between each one of the input layer is going to the hidden layer. Here we show all the connection, okay? But the basic idea that we have input here, and in a sense, the output should define for us what we need as an output for the identification of element, identification of an animal, and so on. So, and what is interesting, that the network architecture that we saw, that we are seeing here, there are many ways of neural networks and different ones. So there's no only one neural net architecture. There are all kind of, and they are evolving. So, and still between you and me, there's no specific, very clear way how to define the network which is the best. Google tried to do all kind of research in order to find out what is the best neural net for specific application, but as I recall, we didn't reach a conclusive output. For example, if you look at, AlexNet is an old net, and here in this field, when you look 8 or 9 years back, it's an old one. So it's interesting that you have, those layers here that exist. Google LNet used to have about 22 layers, while AlexNet, which is a very simple one, have 8 layers. In the recognition, and Minute will talk about it, the AlexNet wasn't very good, error of about 15%, while the Google LNet is about 6%. Okay, so let's look at the example of classification of a vision, and let's say that we have a network like that, and we'll show later about this connection that not all of them have to be there. And if you look, what we are doing, we look at the input is a set of pictures, and we have to identify who is whom, right? Is that the output? I would like to see the result by identification, a specific person that's supposed to be in this group of pictures. And what happened is, if you look at the layer by layer, the output of layer 1, you see pictures like that. They're very interesting, that actually, in a sense, taking part of the data that exists here. Later, on the second layer, we see something that you still can identify some parts of a face. If you go to the next one, you get something more specific, and then at the end of the game, you said, yes, I found here Jonathan, which was one of the pictures that you see here. So this is the concept of a vision, and from here things are getting much more complicated. So the question, okay, so there are a couple of things here that I won't get into, and the question is, as we said here, there are inputs, and then we multiply by weights, right? We showed it before. As you remember, this W0, W1, those are the weights. And the question is, how do you multiply it? And we have somehow to teach the network to do the job by creating those weights, the right weights, right? So doing that, it is one. And second, in order to teach the network what are the weights that exist here, definitely what you have to do, you need to have a big group of inputs that will tell you what is right and what is wrong. And this is what was done in the industry, which is the ImageNet. It's an image classification. The classification is only for small picture of 256 by 256. There are about 1,000 classes. There are 1.3 training, and so it's a huge amount of pictures that for each one of the pictures, there's a title or there's a classification that we are providing. And when we go and run this in a system in the training, and I won't get into training, but when you run into training, you can change the weight of the filters that we have here in order to get the right solution that it's classified in this kind of pictures. So this is, remember, to take about 1 million of pictures here and to classify them, by hand was a huge huge change in the using of neural net, because suddenly you have a set of a lot of pictures that you can teach, quote unquote, teach the neural net to identify. Let's see. So I think let's stop here. We are on foil 60. Let's stop here. And I think what we have to do, let's take a 20-minute break. Is it okay? Amalia?
Yes, so 20-minute break would be at 10 to 11, okay?
10 to 11.
Test time.
Okay, so let's continue at 10 to 11.
Okay, wonderful. See you all.
Thank you, guys.
Bye-bye.
Amalia?
Yes, Uri, we can start now.
We can start. Okay.
Welcome
Okay,
back,
guys.
everyone.
How many are? Okay. So we can start or continue. Okay. So we'll continue. By the way, we have now another about an hour and a half or so of presentation. Please prepare your questions because I like to keep about 20 minutes to half an hour for Q&A if you have any. So let's talk about we talked about DNN, and a subset of deep neural net is convolutional neural net. It's a deep neural net, as we said, but there are convolutional layers. That means that, not every layer is connected, every element of the layer is connected to every other element in the other layer. Here in this case, in order to get the result in one element of one layer, I need only a limited element in a previous layer. And there are all kind of technique like pooling and so on, but I won't get into details here, just to give you the overall view, and you can read it in Z and Joel Emmer's book, which cover pretty nicely all the concept of neural net. So a convolutional layer, what we have, if we look at the input layer, the feature map, we call it, a layer, and you have the output feature map. Here, what we take the filter that exists here, right, with weight, different weight. The size of the filter is R by S, and actually we multiply the value of the elements here by the weight, sum them up, and bring it to one element, which is the output element activation. So in a sense, what we see here, we have one layer, right, with the H times W size, and we get a new layer with the E times F size. And actually what we do is each one of those elements is the convolution of the filter and part of the input F map. And that is the same, it's being produced by the concept, by the basic element that I show you a few foils ago. So that's where we are. Now, in order to, in many cases, we are complicating it even more. We have not only one input map and one output map, but we have several input feature map, different ones, and the same thing, we have different filters, and all of them, the different filters, each one fits input feature map, and we do the calculation of each one of the filter time input map, and add all of those input maps, multiplication of filter towards one output. So there are many input channels. We can do it, the input maps, for example, can be colors, right? One example that, a different filter I provide to different colors of input map, and the output map is the next layer. So that's a regular convolutional net. Again, we are showing here AlexNet, it's an old foil. There are, in AlexNet, there are about 5 convolutional net out of the overall net layers that exist. There is a fully connected layer in which each element of the previous layer is connected to all elements of the next layer. Usually the fully connected are mostly at the end, right? But there are 3 of them. The number of weights, this is number which is very, very important, is the number of weight of those filters that we look here, right? All the weight that exist in this example of AlexNet is 61 mega weights. Yeah. In general, what we see lately, that the weights are 8 bits, so we are talking about 61 megabyte. And the number of multiply accumulate that exist here is 724 million. Quite a lot. And the nonlinear function that we were looking at, the basic element of the computing, it is being used by the value. So there's an example of one network, a simple one and an old one, not a very good for vision today. VGG16, for example, have 13 layers of convolution. Fully connected are about 3, not about, but 3. The number of weight is pretty high, 138 megabyte. And the number of computation is 15 giga operation, so of MEC, of multiply accumulate, versus 0.7 in AlexNet. Here we talk about 15, 20 times higher computation that needed, and also quite a lot of data that we have to keep as weight. What is the most important thing, and what I would like to show here, that we see more and more convolutional layers in vision machine learning. And the basic idea is that usually the correlation is local. If the correlation is local, and there's no reason why to take one layer that will be fully connected to the next layer, but usually the element around, there's some kind of localized behavior, so convolutional net is good enough. Okay, so here we are in the last part of the talk. Here we are going to something that we, as a research group, is working on, more specific. And so you can see in the reference, there are several papers that we published. But the concept is, again, to try to improve efficiency of machine learning research. And I'll try to show you also the concept, how to approach this kind of research cases. So, a typo here. So let's go up. The matrices that we see in inference neural net, by the way, for your information, most of you know, the inference and there's a training. The inference is basically taking the information that exists and already have all the weights, and the output is kind of a vision recognition, while the training activity is much more heavier, and the purpose is to define the weights that exist in the filters. So we are talking now about vision and inference element. And you know, first of all, what are the matrices? So the matrices are, first of all, accuracy. And there's a database that show you the ImageNet. There are million of pictures with title each one of them. And the question is if the network could identify all what it needed in a high accuracy. Today, by the way, we are getting, at least for ImageNet, that we are getting accuracy which is higher than the human being vision accuracy. So just for your information. Speed, the question is, what are the number of max? And I just show you in Google 16 and AlexNet, you know, how many max are needed there. What is very important is the storage footprint, the number of weights that exist. And this will bring us to a specific solution that I would like to show you. And the bottom line is the energy. And if we talk about inference, those are the machine learning elements that are and will be in you know, near each one of the cameras, security camera, robot camera, and so on. Those are elements that in autonomous car cameras and so on, that is very close to the information data. And what is needed, since it's really not in a warehouse where, you know, or data center, energy is very important. Also, energy is important in data center, but in general, on the edge, we are very sensitive to energy because the data or power source not available always, and the extreme environment of heat and so on is not very friendly when you have high energy. So let's machine learning approximate characteristic, and this is something that you have to know and remember and vision when we are talking about inference and we talk about edge devices. The size of input data is about 10 to the power 6 a byte. This is for one image. You remember that we are going to grow a resolution of images into a neural net, and you know, we have already, you know, TVs and so on in 4K and even more. And the size of the data input will continue to increase. We like to get better and better accuracy of our recognition system, and for that we need a higher resolution inputs, and this will grow. The amount of computing is about 10 to the power 12. Operation is multiply and add, but this is the range of operation we have. In a minute we'll talk about it, and I'll show example. The size of weight is at around 550 megabyte, which we have to look at it if this is a stable number, which can drive us towards a specific implementation. Power constraints, since we are talking about edge devices, they have to be super low power, you know, 10 watts max. And when we look at training, the process of training, which I didn't talk about, which is a process, a very long process of train a system, the size of data is much bigger. 10 to the power of 12 byte. The amount of computing is 8 order of magnitude higher than the edge device, 10 to the power 20. And because of that, when we are running a training a system, it takes a huge amount of computing power. And the power constraint mixed around, 100 watt for a specific die, if we talk about systems that are implemented in ASIC. So altogether, there's an urgent need for energy efficient machine learning, because we are talking here about increase of the computing requirement, and definitely, as I said, the demand of computing will grow. Everybody is with me?
Yes.
Oh, so there's some voice with me. Okay, thank you. So let's go energy efficiency in general. And the question if we can improve. Can we improve the energy efficiency of machine learning architecture? And I divided into 3, right? And I believe that, you can divide it to even more. One of them is reduction in computing. Let's say that we'll build some kind of system that needs, or network that need less computing. We'll talk about it. I'll give you 2 examples. One is the pruning and one is quantization, in which reduces the computing requirement and we can live. The other element, which is super important, which is orthogonal to computing, is the reduction in data movement. And the question is how we can reduce the move of data, or moving. All of us know that moving of data is very costly, and we like to reduce it as much as possible. One idea that is related to is quantization. The minute we reduce the size of the data that we have, we definitely will pay less in energy of moving this data. Compression is a good example. And the most important one that I would like to show is pipeline versus batch. When we talk about neural net, as we see it in theory, and the question is, how do you implement it in architecture in real life? And there are 2 ways to do it. One is the pipeline, and one is the batch processing. And the question, the last one is efficient usage of the hardware resources, and we'll show a pretty extensive research that we did for simultaneous multi-thread. They apply it to neural net, but that will come a little bit later. Okay. Accuracy, and that's a super interesting and very important graph that is related to vision. And we are on the vertical axis, we talk about top 1 accuracy. This accuracy of the top 1 out of the 1 billion that we have. And what we try to see, what is the accuracy between 50% and 80%. And the AlexNet that we showed in the past was at around 55%. So 55% of the cases were identified by AlexNet, right? And later we saw different other networks, all kinds of networks. ResNet is very well known. When we have ResNet 50, and we have ResNet 18, and we have ResNet 101 and ResNet 152. What is important in all those networks and the VGG and so on, that the size of the of the circle here that exists say about the number of weights that exist. What is super interesting and super kind of surprising is that what we see here, that we reach here kind of a plateau in accuracy. And by the way, this accuracy that we reach here, around close to 80% is better than the human accuracy identifying objects. What we see here is that suddenly we see that the size of the weight or the amount of the weight is needed is kind of saturated at the range of about 50, 60 mega element. By the way, the example that Google did, the VGG and the VGG 16 and 19, which require much more weight, the accuracy is not as good. So if this is really the trend, right, and we may get probably a little bit more accuracy in the future, but if the trend show that actually the number of weights that needs for those networks that do recognition of object, it's around, let's say, 50 or 60 megabyte. This is a very strong message. Remember it, we'll come back to it in a couple of minutes. So there is a major message here in this foil that show that actually, by the way, the x-axis is, you see the number of operation in general in giga operation per second, a giga operation, sorry. And by the way, one thing that you have to understand, that the minute will go to higher resolution, the number here will grow dramatic. So remember that the number of operation will grow linearly with number of pixels that you have on the input picture. So we'll see here a grow in this number, and what we believe that the filter size will stay at the range of between 50 and 80 megabytes for this specific networks. So that's one. It's very important to remember because we'll come back to it. Another, a very basic foil that it's very interesting to think about and talk about it is a graph that shows that energy efficiency, right? This tops tera operations per watt. Okay, this is a vertical axis, and the horizontal axis is the throughput. The throughput is the giga operation per second. And what we can see here, by the way, in order to get what is the energy efficiency in tops per watt, what is the basic element of computing that we are doing in neural net, right? It's those multiply, accumulate operation. Let's look at if everything else doesn't cost me any energy, what will be the energy efficiency in tops per watt if I know what is the amount of energy that I'm using in order to compute one operation of the multiply, accumulate element. So when we talk about the 45 nanometer process technology, if you look at the Mach operation and you try to identify or to calculate what is the energy that required to do one Mach operation on 45 nanometer technology, we're getting about 0.1 picojoule per operation. And it's very interesting to to go from picojoule per operation to go to tops per watt. It's actually exactly the same. And what we are getting here, right, is that the number here, the tops per watt, which is 10, is related to 0.1 picojoule per operation, which is super interesting. So when you talk about 45 nanometer technology, and you said, what is the best tops per watt that you can get? Just calculate or find out what is the picojoule per operation of the multiply accumulate, and you get number which is the highest tops per watt that you can get in specific system when not include any overhead. Any overhead means bringing the data to the MAC element, driving the data out, and so on. Writing to memory, and so on. So remember one thing, looking at this graph, when you know what is the picojoule per operation at specific technology, you can say you cannot get better than energy, tops per watt, specific tops per watt. By the way, if you look here, remember one thing, that here, when I'm talking about the 0.1 picojoule per operation, we're talking about 8 bits. When you look at here, what you see all kind of networks that the accuracy is, 16 bit, 8 bit, 4 bits, 1 bit, and so on. So in general, again, if you'll see something that it's more than this line for this specific technology, probably it's wrong. So anyhow, so look at what happened there, or the power per or energy per operation is lower. So this is where we are, and as you can see here, the one over the energy per operation is proportional to energy efficiency with tops per watt. But very interesting graph, and remember that the minute we have this element of energy per operation, all the overhead will reduce this number. And today, in 8-bit, in current technology of, let's say, 16 nanometer and so on, we are getting something like around, between 1 and 3 tera operation per watt for the best neural net system. Remember that the numbers that you are getting here are not considered the number that I showed here, a number for 45 nanometer. Okay. So I hope we understand that. Remember, the minute we include the overhead, which is data movement and efficient use of the execution unit, this will drop. Okay, so let's talk about reduction of computing, and let's say how what this will give us. So first of all, what is super interesting, and it is interesting to see how important it is that the data that we have in machine learning is very, very sparse. And if we look at the sparsity here of different networks, and we are talking about the data in all the layers, what we see that about 60% of the cases that we have, the MAC operation is idle, meaning one of the data inputs, either the weights or the data from the different the previous layer is 0. Meaning, if we build a neural net system when we provide for each multiply accumulate, we provide a Mach engine. 60% of the time it will go idle, and we'll show in the future in foils a case like that, at least one. The about 20% of this is around a partial utilize, meaning, let's say that if we are talking about 8 bits Mach operation, let's say that the 4 bit of the most significant or 4 bit of the least significant bit are 0, meaning that I don't need to do a multiply of 8 bits. If I know that, I probably need only to do a 4 bit. So 20% of that, and what actually real multiplication and addition of 8 bits times 8 bits is about only 20% of the cases. So it's if you look at that, it's a very strong message that you have here, that we don't have it in a general purpose computing. So here we have a lot of data which is 0. A lot of data which is 0 means that the efficiency of engines, if we won't do anything, the efficiency of using engines won't be very high. So that's interesting. Okay, so we talked about it. By the way, we can see here that there are all kinds of networks. In all of them, sparsity is a major case. Okay, so okay, what is the solution or partial solution? We can reduce the operation, and reducing the operation can be done by pruning, quantization, and value prediction. And probably there are other techniques which are there, but less important. Pruning is the first one. And the pruning is saying you get the network, and what I'm saying, that in some of the elements in the network are not so valuable anymore, and I would like just to ignore them. So it can be weights, it can be rows, it can be filter, can be channels. And the minute I do that in pruning, I'll say, okay, let's eliminate part of the elements that exist in a neural net I have. What I can do is actually to train the network to manage this elimination of elements as part of the network. So this is what we are doing. So less number of weights, because we eliminate several elements, and because of that we are using less weights. But what we are doing, we actually take and train the network to train the new network that I took out several of I eliminate some of the elements that exist there in the weights, right? So this one element, and we'll talk about it more, but in general, when you do pruning, usually, in most of the cases, you like to teach the network to do another session of train weights in order to get back to the accuracy that you used before. But in this case, your inference system will have much less multiplication or max to be performed. The other one is quantization. Reduce the quantization. We started the neural net with a floating point 32. We went down to integer to 16-bit, and now we are in 8, 4, 2, and so on of quantization. And in this case, you know, we are reducing the number of bits per weight. Here we just in pruning we are just eliminate those weights. Here we are actually reducing the number of bits per weight. And here again, you usually, in most of the cases, not always, but in most of the cases, you like to train the system in order to get back the accuracy that you want to reach. Another technique that we are using to decrease the operation is what we call value prediction, something that a paper we published. In general, what it said that since DNN are statistical base and there is a spatial locality, we believe that the value prediction can be used, and we show a couple of examples. Okay, so so this is the value prediction. So these are the three, and let's go and go to pruning. So this is example that we have before pruning, and then somehow we decided that there are lines like this line, right? That we said, you know, the value that it produces is not large enough, and we just eliminate those lines. So out of these 1, 2, 3, 4 lines are coming from this element, only one of them is being used, going to the last one in the next layer. Once again, you can decide which line to prune, and by that you define what is the accuracy that will be before and after training. But in general, when you prune the lines, right, that you have here, you create a situation in which you can also prune the neuron. So for example, if this neuron doesn't get any input, there's no reason to keep him as part of the new network. And after pruning, actually what we do, we both reduce the synapse and the neuron. So for example, here we took off the neuron, the second neuron, which was here, and the middle neuron, which is here. So these are the network pruning as an example. And if we look at the higher level of pruning, there are all kinds of ways. Now, if you go to a deeper detail of the network, you have all kind of, you can do this, in this case, is the unpruning filter. You can go and do pruning of weights. You can do pruning of rows. You can do pruning of channels. Remember, there are several channels here, right? And the filter pruning. So there are all kinds of pruning. In pruning, as I said before, there are two ways to do it. One, you do it when there's no accuracy impact, so you don't have to retrain it. And in some cases, you have to retrain. So here's an example. Eliminate the computing to reach a target. So in a sense, what you do, you said, okay, I'll eliminate several the element, both element synapse and neurons, and then what I'll do, I'll retrain in order to get back the accuracy. So this is an example reduced parameters and retraining. So we are taking part of the element out, right, in a specific way, and retraining. So what we see here, look at the number of parameters that we have. For example, 2,500, right? And this is log of mean square error, which is related to the accuracy. So it's pretty low here. But the minute I cut the number of parameters and reduce them, what happened, the log mean square increases dramatically. While I'll do training of the system, I'll be able to get down to almost the same accuracy that I have before. There's a little bit of degradation in the accuracy, but as you can see here, we reduce the number of parameter in a factor of 2 or 2.5, and the log mean square change not much. So this is the concept of pruning that's being done in most of the cases is being done statically. There is a case that when you do pruning, you eliminate without reaching your accuracy target. You go and you reduce parameter and retrain, and you choose the weights to be ignored. There are several techniques, and there are several papers on that from long time ago, right? Remove those weight and synapse, and you retrain the system. In many times you can reach no accuracy impact or minor accuracy impact. Now, okay, so we finished the pruning part. Let's go to quantization. This is a big area in which many researchers are working. Preceding is actually the number of bits that represent the data, and the number of bits is a log2 of the number of levels that you present the value that exists there. And the quantization is actually trying to map data to a smaller set of levels. Instead of having, a log2 number of levels, we can actually get a less bit that will present it. And, there are two ways to do it, the linear and non-linear. And we'll talk about it for a while. So we use a precision. Remember, and now we're talking about linear. So the move in the past, we started with floating point, reduction to fixed point, didn't change much the accuracy. The bit width reduction, and there's another option, which is a non-linear quantization. By the way, if you look at the 32 floating point example, and we went down to 8-bit fixed, and even there are some people that are showing some interesting result on binary. So this is the concept of reducing. Now, the question about quantization, the non-linear. So here we reduce the quantization, but by reducing the number of bits. Now we are looking at an interesting example. The distribution of signals or data is usually, if you look at the weight values, it's around 0, and in most of the cases, a kind of symmetrical. But in general, what we do usually is a linear quantization, meaning that for each level with a specific distance, we provide a quantization, or we check how many signals are there. So in general, if you look at this case, although most of the signals are around zero, there are also some, at least by doing linear quantization, we have here some representation of data that actually doesn't exist. And in many cases, people are talking about nonlinear quantization, and in this case, a log 2 of a quantization, a quantizer, in which we're saying, since we know that in this area there are not so many signals, let's widen the distance between the element of quantization, and we'll keep a much higher dense of a level of quantization around the peak of this distributed function, and it's worked pretty good. So they use it. There's a lot of papers in this field. If the messages, here's the conclude messages about pruning and quantization. So what we see here, again, this is a quantization or the accuracy loss, or the vertical, and here is the model size, right? After we do a pruning quantization or even SVD. So this is a reduction in the model size, and this is the accuracy. And we see cases when the red ones show pruning and quantization. And what we see that as long as we reduce the model size in about 7%, we are not using not losing a lot of accuracy, but and the same we can look at the pruning only and the quantization only. So that's the idea that the axis here is the model size ratio. Okay. So we can see that we can reduce dramatically the model size when we do a pruning and quantization here without losing, the accuracy loss. And it's interesting. There's a nonlinear here. There's another example, and here we have the weighted value. And here, in case that the distribution is not so symmetrical and so on, you can make a decision, where to sample those levels and to get pretty good results on it. Definitely, what you have to know the distribution of the signals or the data that you are working with. So that's super interesting, and the question is how to reach them. Okay. So, and of course, in most of the cases, remember that we have to do retraining. It won't work without it, or will work not so good. Value prediction. This is some work that we did, very interesting, and I'll stop here for a minute to tell you what we are doing. What we're trying to do in our research in general, we're trying to look at basic concept that we used in the past in our old computer architecture, and try to apply it to the new environment, in this case, machine learning. One of the things that we did is value prediction. In the past, there were a group of researchers working on general purpose architecture that talk about value prediction. Value prediction try to identify or to predict the data that exists somewhere, let's say in memory, and instead of going and bring it from far away, from far memory, try to predict this value. This value prediction work pretty well when you talk about addresses, value of addresses that exist in memory. We know about stride access to memory and all kind of patterns that you can predict what will be the next one. It was less successful when you look at values, general random values. So here we said, wait a minute, let's look at the machine learning and let's see if in the machine learning, there's some kind of characteristics that we can leverage value prediction with. And surely enough, we're looking at the vision machine learning, there's some kind of a spatial locality. That means, when you are looking at the wall, and definitely you want to calculate something that exists in a constant color wall, that, the operation that you do in one element is very similar to the operation that is around this specific element, this kind of a spatial locality of value that exists there. So we said, let's try to do that here in value in the neural net, and this is an example. So we took a kind of this is a part of the element that we have in 5 arbitrary filter channels, right? So the different layers, and what we can see here, the black in this graph means that the picture is white. Sorry, it was easier to show it this way, and you can see that there is a lot of black areas, and if I calculate one of these elements, the black one, there is a good potential that its neighbor is also black. And the question, this the feature map, the output feature map before you compare or compute. And what we decided to do is say, let's take the 4 pixels that exist here, right? Or the 4 activation that we have here. And we'll only calculate the diagonal in that direction. And if the 2 elements of the diagonal are identified and they are 0, what we'll do, we'll predict that the other diagonal elements are also 0. So we are predicting based on spatial locality. Since, in general, in neural net, the neural net is very resilient to some kind of small errors. So in the case that we'll miss here, probably we'll get some impact, minor impact on accuracy. And this is what actually happened. So what we are doing is that, again, we take the activation, we calculate a full activation on the diagonal of these 4 elements. If both of them are 0, we predict that the other 2 are 0. If one of them is not 0, then we calculate all the 4 elements. And this is an example of this one, right? The middle one, what we see that one element is 2, one element is 1, and that means that probably what we have to do, there's no spatial locality, and we have to calculate the other elements. So here you can get that in the first line, we didn't have to calculate the element in the other diagonal, and the other cases we had to do. So it's very interesting. It's working, not perfect, but we check it since we did it long time ago, as you can see, 2 years ago, even more than 2 years ago. We did it in all kind of networks which are not being used anymore, the ResNet 18 and VGG. And we got interesting results. Something to, as I said, to write a paper, but something that needs more research on it. But it's interesting because what we did here is something that, I like to raise the flag here, is to look at some techniques that exist in the past and try to apply them to new environment, which in our case is the neural net, and the spatial locality calls for use the concept of value prediction that we used in the past. So this is an interesting one. Let's go to the second part of reduction in energy, which is a reduction in the data movement. And here there is a super strong message. I'm just giving the edge of the concept, and but there's a very strong impact to this message. So we're talking about pipeline versus batch. First of all, look at all kind of network that we have, right? We can say how many, convolutional network exist. These are the LearnNet 5 and AlexNet are old ones. The more new ones are ResNet, and are even more new ones. But what we see that we have more convolutional layers, and more we can see more and more convolutional layers. So out of, for example, on ResNet 50, out of 15 layers, 49 are convolutional layers. And also what we can see that we talked about it in the past, that the number of weights are not that big. In ResNet 50, there are about 24 mega weights, right? Each one is a byte, and we can say, what is the number of operations that exist there. So a bottom line, convolution layer are important, okay? And we can see them dramatically almost everywhere. And the weights may be kept on die. And this is actually bring us to pipeline. Now, we'll try to make you think about it. We won't go to detail because the time doesn't permit. But let's go to the highest level. Batch. Most of the neural nets, not all of them, but most of them are working on a batch mode. And what is the concept? The basic concept is that in a DRAM, you keep the weights that exist. And what do? You download the weight to the MAC cluster, the multiply accumulate cluster. And what you download the inputs and you start to calculate one layer of inputs in order to get all the outputs of this layer. You finish it, you write it back to the DRAM. The main problem, if you would do it only for one picture, then, and then you don't use efficiently the download of the filter information. So what most of the system are doing, they use a batch. What does it mean? They have several pictures to do recognition of. They download once the weights, and then they put the input of picture 1 get the output, put a picture of network of a picture 2, right, with the same weights, write the output of this layer, putting another input by another picture to layer to the layer, and so on. So in general, what you do, you take the weight, keep them stationary in the MAC in a MAC cluster, and bring several elements of input and write several elements of output. In this case, why they did all those this concept? Because they say, you know, if we'll try to do several layers or all the layers in the same time, I have to download all the weights, right, of all the layers, which is a pretty high number. At least it was expected. The number of filters will be too high to keep on a die. So, but this is the batch operation. The batch have some advantages that in a sense of efficiency, you download once the element and then you get several batch operation. But remember, as a consequence of adding, let's say, 512 batches to this concept, then the latency of operation of all the network is actually multiplied by about 512, because you do the first layer 512 times, the second layer 512 times, and so on. At the bottom line, the latency will be high, and you have to be careful. In some cases, latency doesn't help you, definitely in autonomous car and so on. So this is one way of doing it. Most of the people are going in that direction. The other concept is the pipeline. The pipeline is really based on two strong elements. First of all, the CNN is most of the computing. This is one. And the other concept that they're using is that the number of filters that are needed, weights, is limited. And as we show in one of the foils, previous foil, we show the saturation of a number of filters that exist. Now, if it's true, right, and it's true because there are some companies that do that, what we can see that if you take the one output of the network, you can go backwards to the input and say which one of the inputs influence this output. Remember, we are talking about CNN, and CNN have some locality, spatial locality, because it's a filter of 3 by 3, 2 by 2, 5 by 5 max. So in a sense, you can take one output at the output of this network and see which elements at the input impact this output, and start to calculate only those elements. Now you keep MAC, physical MAC, for all the layers. And the idea is that since the number of weights or number of filter is limited, let's say, to 50 megabytes, then you can keep it on die and you can start to work on all the layers because the weights are there, and you start to pipeline. You know, you take some of the inputs that influence one output, you calculate and send the results to the second MAC or second layer, and so on. So in a sense, what happened, this process is a process of pipeline in which data is getting into first layer, Some of it is going out to the second layer, from a second layer to the third layer, and so on. And because of that, you don't need to go to DRAM. Remember, on the batch operation, what we do, we take the data and you write it to memory or to DRAM, and then you go the next batch set, you put the input and you write the output. So you need all the time to get input and get the output, and this costs a lot of memory space, which you can do it on SRAM on die. So you need the DRAM. And as we told you before, going to DRAM is not very efficient energy-wise. So here on the pipeline concept, we have much less access to memory outside the die. And actually, there is you can do everything for vision. For the cases that you have a limited number of filters, right? You can do it on die. And a good example is a company I'm working with, Halo, that actually have a silicon working on the concept of pipeline. The main problem of this concept, that's pretty complicated software compiler that you have to build in order to define exactly who is getting what data at what time. And this is the extreme, it's another topic to talk about. It's the extreme case in which you have to combine both software and hardware architecture to design it together. And when you talk about pipeline, there's a combined complexity of the software and also of the hardware. Very interesting, but can be resolved. And there are some examples that is already resolved. And the bottom line is that the energy efficiency is huge, right? At least the example that I'm talking at the 16 nanometer, 64K max, running at 400 megahertz, wasting about 3 watts. So interesting. It's not a simple solution, but definitely and is specific for the cases of CNN. Okay, so we touch this data access, and here the message in the pipeline is reducing the memory access definitely to the DRAM, which is not efficient. And all the memory is on die. So here we are going to the next part, which will spend the rest of the time of this talk, which is a multi-threading machine or simultaneous multi-threading in machine learning. Multi-threading is a well-known technique in general purpose computing. Super interesting, and we'll talk about it in a minute, and we'll try to show what we did in order to combine this interesting solution that we use in general purpose to machine learning. So simultaneous multi-threading said that you are running several threads to gain performance and efficiency by sharing actually underutilized resources. And in many cases, in general purpose machine, we have unutilized resources. For many years, we know that if you run one thread on a 4-wide machine, general purpose machine, you probably get one instruction per cycle, although potentially you can get 4, meaning this underutilization of resources. yes, there are minutes or second or nanosecond in which all the 4 execution unit or all the width of the pipe is utilized, but in general, it's not, the utilization is not that high. And at that point, the people started to talk about, let's try to run 2 threads on the same hardware. So the general purpose, we share the resources, execution unit, prediction structure, caches, and so on. And actually, it's trying to exploit the unutilized resources. What we think about SMT in machine learning is, yes, let's utilize resources due to data sparsity, for example, and leverage the statistical behavior of DNN. Remember, we are talking about accuracy in percentage. So if I'm losing or statistically don't change dramatically the result should be identical, but with statistical base. And the basic idea, the target is to utilize the hardware. So let's say, so what the message here is that ML architecture is resilience for inaccuracies, which is super interesting and so much different from the general purpose architecture that we used to work with. The general purpose architecture doesn't matter where do you run your program on architecture A, B, or C, you'll get the results exactly the same. In machine learning, there's a resilience to inaccuracy, and the basic idea that the output is statistical based. Okay, so let's remind you about the multi-threading in general, and then we'll go to the implementation that we did. So first of all, it's a thread level parallelism. Multi-threading, we have several threads. You can call it thread, you can call it program, you can call it tasks that you run in parallel. And the basic idea is trying to use a latency event that takes long latency with the existing thread that are ready to run. So they all execute on the same pipeline. Let's say if you have 2 threads, one of them is in green color, one is in red color. The minute one of the element of the green color got stuck because of access, which is takes time, or data is not available, the other thread, the red thread, can use the resources in the same time. So in a sense, it enables you to run the program, 2 programs in parallel or utilizing the resources. And actually, as it's written here, the multi-threading allows multiple threads to share the functional unit of a single processor in an overlap fashion. Okay, so that's the concept of multi-thread, a well-known technique for many years. And this is an example. This example is I think, oh, interesting. The reference here, it's Intel, but I think the reference should have been the alpha of digital. Here we are talking about the pipeline of a general purpose machine. There's a micro operation queue, there's a renaming process, there's another queue here, there's a scheduler, there's a register read, there's the execute element or pipe element, there's the L1 cache access, there's a register write, and this is the retire. Now, if here in this case, we are showing two threads, the yellow thread and a red thread, they start in two different places, two programs, but, then you start to move them inside the pipe, and always there are kind of competition for the resources. The minute at one point, for example, between the register and execution, there are elements of specific thread ready, they will compete with the other thread on the resources that exist on the execute level. And if they collide, one of them will win, but in many cases they don't collide, and by that the utilization of the resources are getting much higher. But before that, just for your information, the same thing that happened with the value prediction, in which I mentioned that the result were less than expected. Prediction of value just out of the blue is not simple. Definitely for addresses was okay. The same thing happened here in SMT. In SMT, although we knew that in general purpose engine, although the potential ability to run n instruction in parallel, let's say number 4, if it's a 4 wide, the potential is there to run 4 instruction in parallel and get IPC, instruction per cycle, of about 4. In general, what we are getting about 1. It's even more than that. The minute we introduce SMT to general purpose engine, we got something like about 20, maximum 30% in performance, although the potential performance was much higher, but somehow because of the complexity of the structure, the idea that we have all kind of prediction element like caches, like prefetch, and so on. The SMT, or hyperthread, they call it Intel, brought about 20 to 30% more performance only. Okay, so here we are talking about a technique, a very nice technique, that for general purpose, the result were okay. Now we're talking about, suddenly we talked about deep machine learning, and we started to ask, wait a minute, since the utilization of the hardware is not that high, let's try to use it, to use the simultaneous multi-thread. So let's go for data-driven SMT. We'll focus on systolic array and matrix multiplication. So first of all, to remind you, what is a systolic array for matrix multiplication? Matrix multiplication is being used for scientific operation, mainly matrix multiplication, but many more. Even part of my PhD thesis was on a systolic array. It's a very well known for matrix multiplication, and was even being used in the TPU of Google. So if we look at the systolic array, it's a set of interconnected processing unit. You can see it here, right? each capable of performing a very simple operation in most of the most of the cases. The PE as a multiply and add operation, super implement, simple to implement, the very regular. You have activation buffer at one side, an omitted buffer in case of implementation for neural net, and actually you do the multiply add and get the result. Each one of the element of the PA, it's a multiply, and of course you have the partial result, and you add it with the last partial result, and at the end of the game, when you finish the computation, you get the results. And as you can see, the progression of the weight is going horizontally, and we can see it here, and the progression of the activation buffer is going in this direction. Excuse me. So this is a systolic array that we are using usually for matrix multiplication. By the way, these are all kind of ways to build it in, output stationary and so on. Okay, so everything is very deterministic in systolic array. Data is coming and moving and not stopping anytime. So you know exactly when data is available at the end of the operation, right? But if there is some zero operation in one of the inputs, the PE is idle. And that's something, and since we know that in machine learning, we have a lot of sparsity, and we showed it in one of the previous foil, we started to think, wait a minute, since there is a systolic array that know how to multiply matrices, and we know that in many cases of machine learning, the sparsity exists. The usage of the PE element is very low. By the way, in one case, I think the first case of the TPU of Google, they talked about between 20 or 30% utilization of the PE element. They use their huge systolic array. So what we wanted to say, okay, wait, if there is a non-utilization, not high utilization of the computing element, how about trying, like we did it in a general purpose, using 2 threads in order to get the output. So what we decided is to take the multiplier add that's missing here, that actually will do the computing. So here we are. Forget about the matrices here. What we did here is a trick in which we said, you can run in 2 threads, but you can also use a 1 thread, divide the 2 matrices in a different, in a specific way, and run them like they are a 1 thread. But that's a simple trick. But anyhow, what we are doing, now we have a processing unit. The processing unit have 2 threads coming in from the activation point of view and from the weights, right? And they're running forward. The only problem that you have here, right, is that, and of course, we share the partial sum register. But what happened here is that the minute the two thread, even if one of the threads input or the activation or wait is 0, there's no question that the second thread can use the PU elements and nothing will stall. But the minute, the two operation of the two threads is not 0, then there is a competition for the resources of the only one multiplier and one addition that exists there. And then for the case of systolic array or SMT systolic array, there is a back pressure that we cause, because the minute the processing unit is being required by the two thread, one of them will have to stall. And you can see here the implementation that we did for the PU element. There is a queue that, in some cases it will fill up. And in this case, you'll have to send a signal back that actually said, this is a back pressure that says stop, because my queue is actually full. So in this case, the SMT systolic array, can be used, but we know that we have to implement some kind of techniques that actually provide back pressure in order to stop the execution the minute the queue, either the horizontal or the vertical queue, is full. So this is the example. So now we can play. What we can do, we can look at the input sparsity and let's look at utilization, right? We randomly choose the sparsity and we try to calculate what is the utilization. The same thing for the input sparsity or the speed versus input sparsity. Definitely when the sparsity is full, there's no problem, to this, by the way, 1 thread, 2 thread, 4 thread, 8 thread. So definitely when you have a full sparsity, then actually what you can, or close to full sparsity, you can get a speed up of all the way to 8 in this case. But what you can see that the minute that the sparsity is at around half, right? Then what we can see a huge drop if you want to write 8 threads instead of what we showed before 2. But for 2, you can get pretty close to what you expect, which is 2x. And the same thing for utilization and so on. I won't get into the results here, but in general, what we did a very thorough research. We did the layout of this element. We showed what are the results that we are getting, how much we are getting in performance, and we look at the area efficiency. And all together, and also we check the energy, and what we got that the energy spent there is at least on integer 8, was not a huge, but it really depends on the input sparsity, right? By the way, you can do the same SMT systolic array for floating point operation, but then the floating operation engine have to be there, and the floating point operation, it's a little bit bigger operation than the integer 8, and because of that, you see the difference between the normalized energy. So, doing that, we said, okay, this is a blocking, but we said, let's go to the non-blocking. And what does it mean? And we said, yeah, in the new environment of DNN, there's a resilience. right? Like, we know that in many cases, there's some small degradation in performance. And if you look even in this picture, as some of you can see, there are numbers that say, what is the percentage probability that this is a bicycle? And what is the percentage of this is a car, right? 0.86 and so on, and so on. So there is a resilience. What will happen if I'll say that this is a bicycle, but instead of 86%, I'll get 87%. So in a sense, there's a fault tolerant to the output of a neural net. So we wanted to use it. So first of all, we said, okay, we'll embrace the resilience. We said, okay, fine. In some cases, seldom cases, when we like to calculate how many cases are there, we'll get a reduction in accuracy, and we like to see what it is. So we said, okay, no back pressure. And then we said, okay, if there is a case in the two elements try to use the same resource, what we'll do now, we'll squeeze them in. What is the meaning squeeze them in? The two elements, the activation and the filter, each one are 8 bits, right? And there are 2 of those. And in this case, we said, okay, when they collide, we'll do quantization. And instead of 8-bit times 8-bit, we'll do 8-bit or 4-bit by 8-bit. So in a sense, what we will do, we'll use the existing hardware to do 2 operations of 4 bits times 8 bits instead of 1 operation of 8-bit by 8-bit. So in a sense, what we are doing here, we temporarily we do quantization in temporarily and in local specific place. Only in those cases that 2 requirements of the resources exist, then we'll go and temporarily we'll change the quantization. And here is we are using the addition will keep the same. So in a sense, what we the concept that it is. So here here's just an equation that show what is going on when we talk about operation. In. What do you do? What do you do? So let's look at what we did as an example, and what we are saying. Let's say that you have thread 1 and thread 2, right? And you have the 8-bit of the activation and the 8-bit of the wait. In this case, right? If these are the inputs, the 2 threads input to one of the make operation or the PU element. In this case, since X of thread number 1 is 0, then we'll do the thread number 2 and ignore thread number 1. So here we continue to use the 8-bit by 8-bit, and actually by that we get the same result as before, and we didn't squeeze in anything, right? In another case here, that for example, thread 1 activation, the most significant bits are 0, right? And the same thing for thread number 2. Here it's very simple. I can use the lower 4 bits of the activation and multiply by the 8-bit of the weight for thread 1, and the same thing I do for thread 2. So again, on this case, we didn't lose anything at all. Here we have an example which is more complicated. Here, the 2 threads are colliding. You can play any game. There's no 0 there, not in the most significant, least significant, or in both. And now the question, how do you divide? So here we did a couple of tricks. One of them, if you look, we have, it makes sense to use only the most significant bit of the activation, right? And to use them and ignore the least significant bit of the activation. In order not to make a big mistake, as you see, the example that we have here, since the least significant bit are almost all of them 1, we round up the number in the most significant bit to 0011 instead of 0010. This is to compensate the idea that we ignore the least significant bit. We gave it a little bit push up in order to get a closer result. And this is the case that this 4-bit, please rounding up, what we call is multiplying the weights, and on thread 2, it stay only the most significant bit. And then you get the result. So in a sense, what we are doing here, right, and so let's go, here we can talk about the least significant bit, but let's jump because we are running out of time. So in general, what we do, in a sense, we are using those squeezing in only in the case that there is a collision. What is interesting is that the speed up that we are getting is the number of threads. So if you run 2 threads, you get, or you build a system, systolic array, that run 2 threads, you get 2x in performance. If you build a systolic array with 4 threads, you run 4x the performance. The question is what happened with the accuracy, and this is what we did. Here's the concept that we were just talking about. Instead of conventional systolic array, we did here a 2-thread systolic array. We call it the systolic SMT. This is the hardware that actually make decision about which part of the elements to use, the most significant list or not at all. And let's see, and this is the results. So what we saw that, for example, for 2 threads, for ResNet 18 and ResNet 50 and so on, we are losing about 0.9%. This is the accuracy that you get with 2 threads. And we are losing about 0.9, 0.3. Here it's a little bit high in Google Net. But in general, as long as you don't lose more than 1%, it looks okay. And of course, if we're going to 4 thread, there's much more collision or many more collision, and the result won't be as good. But then we'll go in a minute to the next step, the time permits. Just for the bottom line of non-blocking systolic array, or SMT, on systolic array, and we checked it on systolic array, but it can be checked for other structure that are not so identical or repeatedly. The performance is, as we said, it's 1, 2, and 4. The bar is missing here. So the speed up is linear to the number of threads that we are running. The energy-wise, we're reducing with 2 threads, the energy-wise with about 33%, right? Because we implement the hardware and we check the energy. The energy area-wise, we increase in about 40%, and the power at about 80% utilization, we got double the performance, but we increased the power only in 1.3. So the result is pretty interesting. And then the takeaway that yes, there's a potential to work with the non-blocking SMT. And these are the final results, about 1% relative accuracy degradation, and about 40% area utilization when you get 2x in performance, which is super interesting. In the coming 15 minutes, I'll try to go to the next step that we did, call it sparsity-aware quantization, which is a little bit different, but get even a better results, right? And I'll show the focus that we did, that weights can be pruned to a structure manner. We'll show how we did it. And logic can be reduced with a number of PEs, and we'll show it in a minute also. And the message itself was that there is a better way of quantize the 8-bit to a 4-bit on the thread collision. So what we did, before we said the minute we collide 2 threads, we somehow decided to take 4 bits out of each one of them, or the most significant or the least significant. This was if there is a collision. Here we are talking about something else, super interesting. This is what we did in the past, right? In the past, this is thread 1 and this is a thread 2, right? And the option was either this one, or you choose the most significant bit when there is a collision, or you use the least significant, or the most, or the least. For example, what you see here, you do some kind of rounding, and in this case, either you take the most significant or the least significant. So the quantization that we did was quantization to 4-bit, but the 4-bit were divided either for maximum for most significant bit or the least significant. The new idea that we came up was, wait a minute, why to choose most significant or least significant? Let's use the 4 bits that has some value. For example, if there are leading zeros, 3 leading zero, why should I use the 4 significant bit and not start to use the value only when the first one exists? So we ignore the 3 0 element, and we add actually the 4 other bit. What do we need here? We need actually a metadata that say that actually we did here a shift of 3, as you can see. So this is the idea. The idea that we have here is that this example of 5 options for 8 bits, and here these are 3 options. So in this case, we'll just check 2 bits at a time. So either this is we'll take the 4 upper bits, or we'll take the 4 middle bits, or we'll take the 4 lower bits. These are what we call a bit spark. In this case, what we do, instead of taking the 4 upper bit or lower bit, here we'll take something in between. What we have to add is the position, right? If we did here shift of 3, if we hit here, we did shift of right of 2, we have to have a metadata that said, this is the data, in case 0, 1, 1, 1, 0, it was shifted to in 2 places. So we combine the 2 concepts that we did, together, and we got pretty interesting results. These are the results of the SysSMT, which I showed you before. And there were cases, for example, of ResNet 18 that we lost more than 1%. When we look at Spark and the idea between the SysSMT and the Spark, remember, the idea there is that what we have is we have instead only 2 options on SysSMT, which is the most significant, the 4-bit, and the least significant 4 bits. In the Spark, we have several options. In the Spark with 5 options, we can have the first 4 one, the other shift 1 of the 4, and so on. In the 3 options, there are 3 options for representing the data. And what we can see with the 5 option, of course, what we are getting is reduction, and this is reduction in accuracy, which is really, really low, right? Even for the 3 option, we even reach a pretty small changes in the accuracy, except for one of them, for exception V3, which is not that good. But in general, what we got is that the Spark is working pretty good. So this is the result we have. Altogether, since we don't have time, it's the 3 options, just for your information, the 3 options seems like the best place to use, not the 5 option, which provide us with a lot of bits or meta bits. Now, I don't know if you can respond, but what we did here in Spark, let's ask the question. By choosing only, for example, here, only the bits that start with 1, but adding a metadata would say how many shifts we did. Anybody have an idea? This is a new representation. Is it really?
So is this not similar to having a mantissa or an exponent?
Exactly. This is actually the same as floating point, right? We change, this is actually a floating point representation, the left one. You're right. Very good. The middle one is kind of a different one, but in general, you're absolutely right. What we did here, in a sense, we did kind of a floating point representation, right? That gave us a better results. That's super interesting. Thank you for the answer, the good answer. The last several foils that we have here will talk about something that we did. We took, some of you probably know, NVIDIA had a sparse tensor core. What NVIDIA did, they look at the data that exists, okay? And they decided that since sparsity exists, what they did, they forcibly zeroed down 2 out of every 4 elements, right, of weight, and in a sense they pruned it. Here's an example. You see a dense trained weight, and now they decided to prune it, meaning they took every 4 elements that exist here and they choose the smallest part and decide to zero it out. So here they zero it out, right? These 4 elements. And now they went and did compression, and then of course they did training. So in a sense, by doing that, they change the number of operation that they have to do by 50%. So they save about 50% of the operation, and this is what they did. So in a sense, the sparse tensor core it took, as we said, 50% of the weight, zero them out, train the system, and then you have a very simple element that actually the number of operation is half. What we decided to do is to add our spark to that system. So in a sense, what happened, they got, NVIDIA got double the performance for the same hardware. And by introducing Spark, we double the performance even more. So actually it's 2x, 4x in performance per existing hardware, because we are using Spark. And as we know, we are using the idea of sparsity, in which the minute they collide, we play the game by doing some kind of quantization. Okay. So it's interesting, and the result is pretty good for the case of Spark or STXC, the Spark tensor core. Okay, so let's jump on that and discussion. So we talked a little bit. And a good answer about what is Spark. It's actually kind of a floating point representation. There is a problem in the memory footprints, because if we do even the 3 option, we still have to add two bits. So instead of being 4 bits, we are 6 bits, which actually need a memory footprint. It's not that we save a lot, we want to save about 25% in memory footprint. So there are interesting solution around, but we won't go into details now. Conclusion. Let's say, so almost 4 hours, whoa, and we made it. The bottom line conclusion. First of all, there's a killer application in front of all of us. Definitely the people that are dealing with computing, and there are a lot of energy efficient ideas to implement a deep neural net, and I believe that there will be many, many more. We are just, remember one thing, we're in the machine learning arena or implementation of machine learning arena in architecture, we're at the beginning. of the era. You know, it's like we have been, 40 years ago in general purpose, that there were a lot of good ideas that we used along the time. This is the beginning of a new era. And there's a huge amount of ideas that will come up in the coming years related to implementation and of deep neural net and usage of deep neural net. We just showed the tip of the iceberg. We talk about SMT and data prediction and pipeline and so on. It's just the beginning. There's a lot of ideas that will come up along the years. Remember one thing, this is what I'm saying all the time to people who are working in this field. Don't try to solve all the problems that exist. Try to solve 80% of them. Remember that, that was my criticism about Intel, that or our general purpose machine. The general purpose machine try to solve all the problems that you have, all the computing requirement that exists, but definitely not in a very efficient way. Try to choose the 80% that actually you need to spend only much less than 80% of your energy and resources in order to get not 100% of the option that you have, you get only 80% of the option. So try to reduce it, and by that, you'll be able to get much, much better efficiency, energy efficiency. And the bottom line, as I repeating again and again and again, we are at the beginning of a new era, and definitely, at least in the neural net area, the solution that you are working should be combined of a compiler or software research together with the hardware. Things are becoming, as I showed you in the case of pipeline, things are becoming very complicated, and the minute and the dependency between the software and the hardware is much stronger or bigger than it used to be in a general purpose. We in a general purpose computing, we used to, the architect designed the hardware while the software compiler guys were doing, things that are irrelated to what we did, or we did things that were irrelated to the compiler. I think that now when we talk about machine learning, the connection and the interaction between software and hardware during the design phase, not only in implementation, but during the design phase, have to be there. Thank you very much. Somehow I managed in this quiet environment to stay for more than almost 4 hours. So thank you. If you have any questions, go ahead, shoot.
Hello, if any of you has questions, please just open your microphone and ask directly. Thank you.
I have a question, if you don't mind. On slide 71, you showed the progression of sort of accuracy over time, and there was a sort of asymptotic growth to a limit of 80% at a certain number of sort of operations. So I'm curious. This is for visual tasks. Does this trend hold for all machine learning, or is this?
No. This is only for accuracy in general. It's only for vision. But we are talking about vision. Only, okay. And I think I said it, but if not, correct me. It's good that you are correct. It's only for vision. Most of the work that I'm doing around is related to this 80%, 20%, and trying to narrow down the scope of things that I'm working. And we decided at this point to look more at the vision. And this one is related to vision.
Okay. So just to sort of expand on this graph, could I read from this that we'll never really need more than 25 gig operations for visual tasks in machine learning? Like, is
No.
Okay.
I think you okay. Thank you for the question. What we see here, right? You're following my cursor?
Yes.
Okay. So what we see here on this line, there are networks that the size is around 65 megabyte or mega weights, right? This is the size. The horizontal axis, my vision or my prediction that it will continue to increase dramatically, because what we will see more high resolution pictures. Remember, all the pictures that they are looking now is only 256 by 256, because the ImageNet that they did, they're looking at the 1 billion or 1 million pictures and put a title to each one of them. They did it only for pictures of 126 by 126 or 256 by 256. And the minute will go for a more precision required system, like, for example, in autonomous cars. You like to see from the far away, you like to see the road signs from far away with a camera of 256 by 256, you won't see it, right? You like to see if from far away, a bicycle rider or stuff like that. So definitely what we will see that the horizontal line will grow dramatically, I think, right? And with, easily in order or two of magnitude. So the number of operations will grow from 25 to 250 to much more than that. Okay?
Yeah, that makes sense. Thank you very much.
Thank you. Any more questions? Go ahead.
Can I ask you a question? Are there any other killer application that where this research about specific hardware architectures is going on? I think about perhaps graphs or other specific algorithms that need this kind of specialization.
Yeah, it's a good question. We were fighting this question almost every year at Intel, when the CEO Andy Grove used to say, "Give me killer app," and we never found them. There was small stuff that we did, right? We did a lot of things, but with the single instruction, multiple data, with the graphics, the media, there were a lot of, but they were not truly killer app, because they were all, kind of, current generation are doing it, but not as good. We can improve it in 20%, 30%, and so on. Here on the neural net, it's totally different environment. It's, if you look at every axis of this environment, it is different. First of all, results should be identical. There's a percentage in accuracy, at least on the vision side, that if you reach it, it's good enough. It doesn't have to be identical. The way you compute, you don't have instructions. It's more data flow kind of architecture. There's a sparsity, crazy sparsity, which you can do. So the new environment that I'm talking about in machine learning has many characteristics different from what we used to. Now you're asking me if there's more. For sure there's more. What are there? I'm not sure. I don't know. You know, there are, as you said, you know, a graph implementation and so on. Things like that have been done many years, and the outcome is not, you know, vivid and strong. So I feel, definitely, I believe that there will be more killer apps somewhere. I cannot identify one that I will say, yeah, this is a big one. Sorry.
Excuse
Okay,
me,
thank you.
Excuse me, can I add something to this? So it's
Yes.
like for this killer application, I mean, it always depends on the context. Like if I unplug my systems from electricity and then you focus a lot of energy efficiency, lots of applications can turn into a killer, right? So it's like if I'm starting to implement, let's say, like smartphone apps, right, which inference neural networks, and within like a minute, the battery is drained, let's say, everything becomes a killer app, right? As soon as I want to give it into a, into a mobile environment, let's say, right? It's like a very practical idea. Like as soon energy efficiency is crucial to actually make something work, like, you know, isn't this then killer application?
It's a good point. I think you're right. I think that the idea of energy efficiency is definitely may bring us to use application that can be done only if you have a super efficient energy. And I agree with you that this is something I was wrong. I think there is a path there, and thank you for your answer or comment. Yeah, I think that the idea that on the edge, in places that we don't use energy, we'll be able to do things that we never did, may create a slew of killer apps. I agree. Thank you.
Thanks.
Hi, everyone. I actually have a question, sir.
Yeah.
You said one of the ways of allowing ensuring data energy efficient algorithm is to use data use and reduce data movement among the layers of memory. And you also mentioned that 50% of the energy that's being used by DRAM comes as a result of refresh. So I'm starting to wonder, is that the trade-off that you get as a result of increase in performance by having the data in the memory?
You know, people are talking about it, and I agree with them that the pressure on memory is growing all the time, and we access somehow, you know, data is growing, big data, you know, we have to approach the big data. Approaching to big data takes us energy. So definitely the main thrust that I can see, or another main thrust that I can see, is towards a solution in memory. And, you know, memory store is a good example that everybody is waiting for it to be, you know, implemented in real life. But it will happen. But the basic idea that that memory creates, or the access to memory create bandwidth issue, one thing, and energy consumption, another, definitely will be a good potential for improving the situation that we are today, and maybe bring, you know, killer apps. I agree. Any more questions?
Oh, thanks. The second question I actually have is, are there tools to measure how energy efficient models are, and if yes, how accurate are they?
Again, can you repeat the question?
The second question is, are there tools to simulate or measure how energy efficient algorithms are? And if they're actually available, how accurate are they?
In general, energy simulation are always problematic. You know, all the chips that I did in the past, we missed the target power because of the, you know, wrong simulation tools. I think we are getting closer much more to the real energy consumption, because our tools are much better than they used to be in the past. But in general, I think that you know, one way to do it is, of course, you know, implementing portion of your big system and try to see, start from a low models and grow later. But I believe that we can pretty good estimate today, the energy consumption. This is my feeling.